So this chapter is about solutions and colloids. And in the first section of this chapter, we're going to talk about solutions in general, what they're made up of, how they form, some of the energetics of solutions, and then we're going to look at two new units of concentration. So you're already familiar with molarity, moles of solute per liter of solution that we used in a previous chapter, but there are a couple new units of concentration that we will use here. So first thing that we want to talk about is a general three-word rule of thumb for chemists, which is like dissolves like. So here we have oil and water, which is something that you may be familiar with, that if you mix them together, they don't mix. They're immiscible. Two liquids that don't mix are said to be immiscible. Well, water is a polar molecule, as we talked about in the intermolecular forces chapter and in the Lewis structures chapter. This oxygen has two lone pairs and two hydrogens, so they're not all domains are the same, and water is polar. Oil is mostly long chains of carbon. Okay, it does have some oxygens in it, but it's mostly long chains of carbon. And these, if you'll recall, are non-polar. So oil and water are immiscible, or they don't mix, because one is polar and one is non-polar. Which brings us to the term, like dissolves like. So what we need to be familiar with is what's alike is polarity. So polar solvents dissolve polar solutes and sometimes ionic solutes. Okay, some polar solvents will not dissolve ionic solutes, but water will dissolve many ionic compounds, as we've talked about when we talked about the solubility rules in the past. Non-polar solvents dissolve non-polar solutes. So for example, if you have a non-polar vitamin, that vitamin is often taken as a little capsule, like say what you'd find in fish oil or something like that, which has an oil itself, the fish oil is an oil itself, and it maybe has vitamin E in it or whatever the case may be, but this is a non-polar thing, which is dissolved in oil. That is usually not soluble in water, just like oil and water don't mix. So as a reminder, we're going to talk about solutes, solvents, and solutions. Okay, typically when we think of solutions, we think of liquids as being the solvent. Now, technically speaking, you could consider air a solution where the gas nitrogen, because it's in the greatest proportion, is the solvent. But commonly we think of liquids as being the solvent, and here I give three examples with water. Seltzer water, which is carbon dioxide dissolved in water. So carbon dioxide is a gas and it's dissolved in a liquid. Vodka, which is ethanol dissolved in water. Ethanol is a liquid at room temperature and it's dissolved in liquid water. And salt water, okay, which is NaCl dissolved in water, and in this case we have a solid dissolved in a liquid. So in all cases of these solutions, we have a gas, a liquid, and a solid all dissolved in a liquid to make solutions. Of course, you could also have multiple solutes. So for example, in seawater, you don't just have NaCl, but maybe you have some MgCl or some KCl. I don't know the exact composition of seawater, but I do know that it's not all NaCl. So there you can have a complex mixture. What's important to remember is that solutions are homogeneous or evenly proportioned mixtures. So if we have here 100 milliliters of this sample that was prepared as this is the solute and water is the solvent, if we have this sample here and there's 100 milliliters of it, if we take 10 milliliters out of those 100 milliliters, we will take 1/10 of the original amount of solute that we had. And the reason that this is the case is it's a homogeneous mixture, which means it has uniform composition throughout it. Okay, the concentration of one 10 millisample and another 10 millisample are exactly the same. And just to review, the solvent is the substance that most retains its physical properties. So in the case of we have a solid dissolved in water, the resulting solution is a liquid. So the solvent's a liquid, the resulting solution is a liquid. If they both have the same physical properties, it's whichever one there's more of. So for some brands of vodka, technically speaking, ethanol is the solvent, because if it's more than 50% ethanol by volume, okay, which I believe some brands of vodka are, then then ethanol is technically the solvent. I don't think anybody's going to ever ask anything about that, but it's just a technicality, because ethanol is a clear liquid and water is a clear liquid. So whichever one there's more of is going to be the substance that is technically the solvent. And the solute is the thing that is dissolved in the solvent. Let's talk a little bit about entropy. And entropy will come up again in a later chapter about thermodynamics. But entropy is nature's spontaneity, or nature's tendency towards randomness, or nature's gradual decline to disorder. So these are simplified terms. Here's the simple idea, okay? If we have helium on this side and we have argon on this side, and the stopcock is closed, then forever helium will stay over here and argon will stay over here. They will stay separated. But if we open the stopcock, these two gases will evenly disperse in the mixture, so that, you know, this is basically half helium and this is half helium and this is half argon and this is half argon. Now, I'm not saying we have the exact same number of moles of each gas, but if we did have the exact same number of moles of gas, they would end up being 50-50 mixture. So why does this happen? Well, this happens because, one, these molecules are moving around. Okay, so these are just moving around randomly, and this random distribution is more statistically likely, which is why we can say, as a simplified definition, nature prefers randomness or a gradual decline to disorder. So basically, these atoms are moving around randomly, and them being 50-50, distributed approximately 50-50, is more statistically likely than 100% helium and 100% argon. Why is that? Well, there's only one state where they're perfectly separated. There are in a lot of states where they're not perfectly separated, right? Because this argon could be over here and this argon could be over here and vice versa. There's lots of combinations where they're mixed together and only one where they're not. So nature favors the more statistically likely. It favors randomness. Now, entropy, a more scientific definition here, is a state function that is a measure of the matter and or energy dispersal within a system, determined by the number of microseconds, often described as a measure of the disorder of the system. Okay, so in a later chapter, we'll talk about entropy a little bit more, and it does have a more subtle definition, and there's some more technicalities. But the basic idea here is these molecules contain energy. Right? They're moving around, they have some kinetic energy, and the more dispersed the molecules are, the more dispersed the energy is in the system. But it doesn't always work perfectly that way, but it's just a general idea. If you want to think about the entropy in terms of a more macro example instead of some atoms, if you think about a house, okay, if somebody leaves their house and they don't sell it and it just sits there for a while, the house doesn't get into better condition. It goes into disarray. And why does that happen? Well, there's only one ordered state of a house where the paint is all where it's supposed to be, all the the trim is all good and all this kind of stuff. And there's many disordered states. So if the paint starts to crack, that's just one possible disordered state. But it's not very likely, statistically speaking, that the cracked paint is going to turn back into the perfect paint. So what happens is it gets more and more cracked, the wind blows it off, whatever the million things that could happen, and the house falls into disrepair. So generally speaking, nature prefers randomness, and entropy is a gradual decline into disorder, or the preference for randomness. Now that we've talked about that, let's talk just briefly about the solution formation energetics. Now, what we want to think about here is kind of this in a qualitative way. We're not actually going to do any math here. We just want to think about what's going on. So in the previous chapter, we talked about intermolecular forces. And what we're essentially trying to do here is explain the concept like dissolves like. So let's think about this. The solute, when we start off, before we make a solution, okay, so if this is some covalent compound, say sugar, okay, there are intermolecular forces holding these molecules together. If it's an ionic compound, there are electrostatic forces, right? A plus being attracted to a minus or a minus being attracted to a plus, so on and so forth. So we have these forces that are holding this solute together. we need to separate those. If we want the solution to form, we need the solute to be less close together because we need to make room for the solvent to come in and dissolve it. So it takes energy to separate out the solute particles. The same can be said for the solvent. The solvent has intermolecular forces. If it's water, it's hydrogen bonding that is holding those solvent molecules together. And we essentially have to separate them to make space for the solute. So it requires energy to separate the solute. It requires energy to separate the solvent. Well, what's going to happen if we form a solution? Well, if we form a solution, we better hope that this new attraction between the solvent and the solute is a positive one. Now, generally speaking, when you form a solution, if it either gives off energy, so it's actually exothermic when you form the solution, or it's only slightly endothermic, the solution will form. But if it's highly endothermic, okay, and these attractive forces aren't very strong compared to these attractive forces and these attractive forces, the solution will not form, which is why like dissolves like. Polar molecules will have strong attracted forces with other polar molecules. So if these are both polar, a solution is more likely to form. Or if these are both non-polar and have dispersion forces attracted with a neighbor, a solution is more likely to form, which is why we have like dissolves like. Now there's one other thing I need to mention here, and you may be asking yourself, well, why does it work if it's slightly endothermic, meaning that it takes a small amount of energy in order to get this solution to form? And the reason for that can be explained by entropy. Here we have more order, right? Because we have solute next to solute and solvent next to solvent. Here we have more disorder because these molecules are mixed together and therefore more disordered. So entropy would drive towards a solution forming, but it doesn't always happen because sometimes these attractive forces aren't very strong and they can't overcome the original attractive forces that we have. So this is essentially the energetics of solution formation. Here's an example of an endothermic solution. If you take ammonium nitrate and you dissolve it in water, it actually takes energy to get it to dissolve. Where does that energy come from? Well, if someone sprained their wrist, it would come from their wrist, right? They would put this cold pack on their wrist and this would draw heat away from the body, which is the whole point of a cold pack. And that heat would be used to dissolve the ammonium nitrate in water. If ammonium nitrate were insoluble, this wouldn't work, right? You mix mix the two together and the ammonium nitrate just simply wouldn't dissolve, but it also wouldn't get cold. So this is just one example of an endothermic solution. There are also examples of exothermic solutions, like things you put in your gloves in the wintertime, you know, to keep them warm, stuff like that. Although I believe that in that case, it actually uses iron powder, so it's not actually making a solution. So a little bit different, but generally the same idea, okay? The next thing that we want to talk about when it comes to solutions in terms of like dissolves like is test tubes with water and hexane. So sometimes we can use two different solvents at the same time. So here we have a non-polar solvent, hexane, which is less dense than water, so it floats up to the top. And here we have water, which is a polar solvent, which is more dense, so it sinks to the bottom. This is basically like oil and water. Instead of oil, we have hexane, C6H14. If we, put a cap on here and we shake this, we can shake these two things together. But if we let it sit for a few seconds, they will separate just like oil and water. The hexanes are attracted to the hexanes and the water are attracted to the water, and there isn't much traction between the hexane and the water, so we don't get a solution. Said another way, these are two immiscible liquids. Well, what happens if we add different solutes? Okay, in this case, I'm going to add NiCl2, which is green, which is why I've added it. Which one of these two things is NiCl2 going to be more preferably to go into? Nickel 2 chloride. Well, it's going to be more preferable to go into the water. Why? Because water is polar and nickel 2 chloride, which contains a metal, is ionic. So therefore, it's going to have a stronger preference for the water. So if we shake these two things together, the hexane will stay clear and all of the green nickel 2 chloride will end up in the water. What about iodine, which is a purple color in solution? Well, if we take iodine and we add it here, Iodine is a diatomic, so it's completely nonpolar. Which of the two is it going to prefer to dissolve into? Well, iodine is going to prefer to dissolve in the hexane, which is also nonpolar, because again, like dissolves like. So we don't get any iodine or any purple color in the water, and we get all of the iodine or the purple color into the hexane because of like dissolves like. So this is basically how liquid-liquid extraction works. Liquid-liquid extraction can be extremely useful. For example, if you take a urine sample of someone suspected to have taken cocaine, and you take that urine sample and you shake it with an organic solvent, the cocaine metabolites are relatively nonpolar and will tend to go into the organic solvent, which extracts it from all the other stuff in the urine, which is aqueous and water-based, which you would not want to inject into the instrument to test to see if cocaine was present. And this is something we teach in our upper level courses. So this is basically a useful tool where we can use preferential solubility, or like dissolves like, to get our molecules in the place that we want them. Unfortunately, it is more complicated than being presented here, but this gives you a general idea of how that principle works. The next thing and last thing for this section that we want to talk about is 2 new units of concentration. So as I mentioned before, you have talked about in the past 1 unit of concentration, and that is molarity. Molarity is moles of solute per liter of solution, and we did several calculations in the past where we used molarity. But now we want to look at 2 new units of concentration, the first of which is mass percent. This is mass of solute over mass of solution times 100%. So for example, if you get, I believe, a solution of, contact lens solution, it'll be 0.9% sodium chloride. So this means that we have the mass of the solute over the mass of the solution times 100. We have a mass percent. It may be a mass over volume percent instead of a molarity. So for people who are making solutions for the eye industry, okay, they find that mass percent is a more beneficial concentration to use. Or, blood alcohol content can be mass percent or mass over volume percent, depending on, which country essentially that you're studying it from. So, a couple really important things to note here. The mass of the solution is the total mass of the solvent and the solute. The next one comes from more of an environmental chemistry type perspective, and that's parts per million, which is very related to parts per billion. And parts per million is the mass of the solute over the mass of the solution times 1,000,000. Okay? Another way of thinking about this is it's milligrams per kilogram. So if you have this mass in milligrams and this mass in kilograms, you don't need to multiply by 10 to the 6 because they're already 10 to the 6 apart. So it's milligrams per kilogram. If you wanted parts per billion, which won't be asked here, but if you wanted it, you just multiply by 10 to the 9 instead of 10 to the 6. Since water has a density of approximately 1, this is how many milligrams are in a liter. So for example, if somebody says, the water is contaminated with 1 part per million lead, well, what that means is there's 1 milligram of lead in 1 liter of water. So that's what a part per million is. So the last thing we're going to do here is go over 2 examples where we actually look at the questions and we solve them. Okay, so let me get the screen up here so that we can do this. So this is the same slide, it's just written out so I can write on it. It says, what is the mass percent of a solution made by dissolving 0.214 grams of solute to make 18.2 grams of solution? So if you'll recall from the previous slide, the mass percent equals the mass of the solute divided by the mass of the solution times 100. Now, generally speaking, we want the solute and the solution to be in grams, but the truth is it doesn't matter as long as they're in the same unit. They'll cancel out and you'll get percent as your answer. So in this case, if we look, our mass of our solute is 0.214 grams and the mass of the solution is 18.2 grams, so they're both in the same unit, they're both in grams. So let's go ahead and plug in. 0.214 grams divided by 18.2 grams times 100. And when we do that math, we find that this solution is 1.18% solute, whatever this, oh, that's a 1, whatever this solute is. Okay? Next one. It says, what is the concentration in parts per million of a solution containing 3.8 milligrams of solute in 1.5 kilograms of solution? So parts per million is equal to grams of solute divided by grams of solution times 10 to the 6. Or you could do mass of solute over mass of solution times 10 to the 6. Okay, so in this case, we need to take the solute and we need to convert that to grams. So if it's in milligrams, we need to divide it by 1,000, which is 0.0038 grams of solute. And then we need to take our solution and convert from kilograms to grams. So we need to multiply this one by 1,000. So 1.5 times 1,000, which is 1,500 grams for the mass of the solution. Then we need to multiply by 10 to the 6, or 10 to the 6 is 1 million. And when we do this, we find that this is a 2.6 parts per million solution. So these are just two different units of concentration that are used in different applications. Okay, the healthcare industry uses mass percent, and sometimes mass over volume percent, where you put the volume of the solution instead of the mass of the solution. The environmental industry is using parts per million, and I'm sure there are other industries that are using each of these two different units as well.